Okay, first of all, let me thank the organizers for inviting me to this very interesting already and very promising conference. So I will talk about some work which in progress with David Kashdan on the classical master equation. So our purpose is to give some mathematical sense to this master equation in the simplest situation, finite dimensional situation. What is this equation and how is it related to critical points, critical sets? And so let me first say just two words of kind of the physical context where this equation first appeared, and then I will explain the mathematical problem we want to consider. So the classical master equation appeared first as classical limit of the quantum master equation. So I will just say some very rough historical kind of words about the quantum master equation, and then I will kind of start the talk with the classical one. So the origin is oscillatory integrals, like integral of e to the I divided by h bar of s0 of x, some function f0 of x on Rn, if you like, dx1 to xn. So, as you know, you can consider this the asymptotics as h bar goes to 0 of this integral. So in the physical context, this is usually an infinite dimensional integral, but the problem is already interesting, the finite dimensional situation. So if S0 has an isolated critical point, then there is this stationary phase expansion, something like some prefactor S0 of x critical point times F0 of x critical point, and then there are some corrections of h bar, if you like. And this is a case where you have an isolated critical point. Now, and physicists looked at these integrals. The Feynman expansion is essentially this story in infinite dimensional situations. And but in quantum field theory, it is often you have symmetry groups and infinite dimensional symmetry groups. So so these integrals are rarely of this type where you have an isolated critical point. So you have non-isolated critical points, and the general question is what to do in this situation. So of course there are many reasons why you can have a non-isolated critical point. One situation of interest is if you have a group action, a Lie group action, and then critical points come in orbits, and you want to integrate over the orbit space. So there are ways to write these integrals as an integral over the orbit space of the Lie space, and again be able to write something like that. So Faddeev-Popov did this in the case of gauge theories, where you have infinite dimensional integrations, infinite dimensional groups, and then you can integrate over the quotient space, and they were able to express, to write down this expansion in terms of Feynman diagram by introducing these so-called ghosts and anti-ghosts. So they introduce some additional variables which encode this construction of integrating over the orbit space. And it was then understood by Batarin-Vilkovsky that actually these procedures of Faddeev-Popov works in a wider generality than just group action, but it works in the situation where the fact that you have non-isolated critical points comes from symmetries, which are some kind of foliations given by some vector fields, which are not fundamental vector fields necessarily of a group action, but you can still do that, and this is the basis of the equation. And so very, very roughly speaking, and I will be more specific in the classical case, you rewrite this as you add lots of variables, anti-commuting variables and so on, and now you write something like e to the I h bar s of x, maybe capital X, because now you have more variables, f of x and dx, and so the point of view suggested by Bataille-Vilkovisky was to understand that this should be understood as some integral over the zero section of some cotangent bundle, odd cotangent bundle, T star minus 1 of V, for some super variety or manifold V, and actually if you integrate over the zero section, you integrate over some Lagrangian submanifold. And the idea of Bataille-Vilkovisky was to kind of deform this Lagrangian manifold from the zero section to some kind of more transversal thing, so that this integral here would make sense, and has an isolated critical point for which you can do the classical expansion. So they were able to understand the Faddeev-Popov construction of integrating of the orbit space as an integral over some bigger space over some Lagrangian submanifold, and the main point was to write down an action S which starts from a zero, reduces to a zero if you look at the zero section, but so that this integral would not depend on the choice of Lagrangian submanifold, so invariant under deformation of the Lagrangian submanifold. And that was guaranteed by some equation which is called the quantum master equation, which is more or less like this, maybe with I there. So there is a Poisson bracket, this is a Poisson bracket on this odd cotangent bundle. There is a BV Laplacian which I will not talk about because it belongs to the quantum world. And so the idea was, starting from something like this, you should construct some S which kind of, as to lower order, is S0, has some corrections, obey this equation, so that formally this integral, when you take L to be the zero section, reduces to this, which doesn't make sense because you have non-isolated critical points, but then it's independent on the choice of L, so you deform it a bit and have some meaningful answer. So the question is, what is this S? How to construct it out of S0? And the first step suggested by Bataille-Vilkovisky was to treat the classical case, namely h bar equal to 0. So the classical master equation and I will make it more precise in a moment, is SS equal to 0. And yes?
In this context, you think of Bataille-Vilkovisky generalization exactly say in the context of supergravity or just some J? This is first, and then what is S in your case?
What is S in my case? So I will be more precise about what is S in my case in a second. I will. This was kind of the introduction, yeah. And then so Bataille-Vilkovisky introduced some very general context where you have this. So you start from S0 and you construct S, and this is what the topic of my talk is: how to construct S out of S0, right, and the construction of Bataille-Vilkovisky was first to construct S, and to this is associated some cohomology, and if some obstruction vanishes, then you can recursively construct S. Maybe I will put an H bar to distinguish it from the classical solution, which starts with S and has correction. So the second step is kind of easier. If you have some vanishing of an obstruction, then you can construct out of the classical, you can construct the quantum. So let me start from the beginning again. So I will start from the data I want to start with is some function S0, which you could think of as a polynomial in n variables, or more generally, a function on an affine variety. Over a field of characteristic 0, for instance, the real numbers. Okay, so you have, say, a function, a polynomial in n variables. And the result of the construction will be a solution of this equation, which will come with some cohomology associated to it, which is called BRST cohomology. Which is given by the with this differential bracket with S. And as we will see, this cohomology will have to do about, we have something to say about the critical set of this function S0. So this is the construction which I would like to describe. And for this, I have to say something about graded manifolds, because the function to construct S out of S0 according to Battaglia-Birkovitsky, you have to add variables ghost, which are variables of degree different from 0. So it will live on a super or graded manifold. So let me introduce the notion of graded variety as we need it for this for our construction. Varieties. So there is this kind of general definition that I would like to say. So you start from X, some non-singular, smooth, affine variety, say, but it can be more general. And then a graded variety with support or body or something X is a locally ring space so you have a topological space and a ring of function, let me call it V, and OV, so this ring of function on it is OV is locally is some completion of the sections of some graded vector bundles. So you have and E is a locally free sheaf. So it's a vector, sections of a vector bundle. So you have a finite rank. So you have a vector bundle over X, or X module over X, and so it's degraded, and each component is kind of has finite rank, finite dimensional vector bundle. But you could have all components in positive and negative degree. And I have to say about this completion, because this is a little subtle point, sorry for this technicality, that so what we write. So you start from the symmetric algebra of E. So what is a symmetric algebra? You take polynomials in sections of E, and but with the sign convention. So the odd value. So this is, you take the tensor algebra of E over X. Modulo, you have X, Y equal -1 to the degree of X times degree of Y, of Yx. So it's a graded symmetric algebra of E. And then, so this is graded by the total degree. So you sum all these degrees. And then you have a filtration Fp of sim E is an ideal in this algebra generated by elements of degree at least p, for p 0. So this will be a descending filtration. You have F0, which is sim E, and it contains F1, contains F2, and so on. And we take the completion with respect to this filtration, but degree by degree. We want the completion to be a graded algebra. So the degree I component is the inverse limit of sim EI modulo Fp of sim intersection sim EI. So it is a completion degree by degree. So this is, I'm sorry for this technicality, but I think it is a little important. Okay, so in something like this, the solution of the master equation will be defined. So this is a graded variety in our terminology. So and then we say that V is the non-negative graded if OV, the components of degree I, is 0 for I smaller than 0. And if you have a positive, non-negatively graded variety, you can construct the cotangent bundle, the shifted cotangent bundle, which will have positive and negative degree. Will be the pair X and maybe M, I will call it M, is M, and the symmetric algebra of the tangent sheaf to V. So this will be the derivations of the structure sheaf with the same completion. Okay, so this is a cotangent bundle. And this cotangent bundle comes with a bracket, which is essentially I will try to pronounce it correctly after the course of this morning, Schouten Nine-House bracket. Okay, so in this notation we will have a product. So this will be a sheaf of so-called P0 algebras. So we have a product and a graded commutative product of degree 0 and a bracket, a Lie bracket, with Poisson bracket if you like, of degree 1. Okay, so now I can define what is the classical master equation. Will be, so the bracket will be denoted by this, will be S equal to 0. And S is a section of this T star minus 1V. So if you have a Z, a non-negatively graded variety V, the master equation we will consider are sections, functions on this T star 0 of degree 0, this is degree 0, which obey this equation here, which is non-trivial because the bracket is symmetric on degree 0. So this is a Lie bracket in the graded sense.
The bracket is induced by the structure of the cotangent of the
right. It comes from, so on the linear part here on TV is just the bracket of vector fields. Right, so maybe I will, so maybe the basic, maybe let me say the basic example. You have this, we call it OM here, not to write the whole thing. Will be the global sections, at least will be, you take functions in variables x1, x1 star, x2, x2 star, and so on. And the degree of xi will be the degree plus the degree is equal to -1. And you have finitely many variables xi in each degree, but you could have infinitely many variables. And the bracket is defined so that xi xj star is equal to delta ij, and all other brackets are 0. And here, of course, you will have to complete, which means that you take in each degree, so you take formal power series, but with but all terms in each formal in all monomials in the power series have the same degree, and then you take the direct sum. Okay, so this is the story. And then if you have a solution of the master equation, then you have the BRST complex. Which is a complex of sheaves, if you like, which is the functions and the bracket with S. The fact that SS is equal to 0 means that this is a bracket. Okay, so this is a sheaf of differential P0 algebras. So and now the construction of Bataille-Vilkovisky associates to a function, say polynomial in n variables, it will associate such a complex of P0 algebras, and this is what we would like to understand. Maybe I should continue here. Right, so let me say again some kind of basic property of this shifted cotangent bundle is that they come with some kind of canonical coisotropic submanifold. Namely, if you take, let me give it a name, so if you take IM, which is F1 of OM, so this is the ideal generated by positive elements of positive degree. Then it turns out that this is easy to check, that this is coisotropic, namely the bracket with itself is 0. So, and then you can also that in particular that S will be invariant. If you have a solution of the master equation, you will have this, and so you can consider this complex here, which is OM by IM. So this will be negatively graded or non-positively graded, and the induced differential. So this will also be so if you can think it geometrically as some kind of canonical coisotropic submanifold with a cohomological vector field on it. And so now let me introduce, so our main result is that under some assumption, if you start with some function S0, some polynomial in n variables, you can essentially canonically construct a solution of the master equation and the BRST complex. Yes? It included in IM, yes. Thank you. Sorry. And for this we introduced the notion of BV variety. So let me explain this definition. So again, you have X an affine variety non-singular, affine variety over a field of characteristic 0, and you have a function on X. And then a BV variety with support X and S0 is a pair VS where V is a non-negatively graded variety. We support X, so it means that the degree 0 part of the functions are functions on X, such that, and S is a section, is a function on this odd cotangent bundle. M is a cotangent bundle of V. I should write it. Shifted cotangent bundle of B, such that, and maybe I need more room to write the conditions. I will continue here. So, and this is of degree 0, we write it here, degree 0, such that so the first condition is that the degree 0 part of S is a given S0. So S is equal to S0 modulo IM. So modulo IM, the degree 0 part of this is OX, so it's a function on X. And then the classical equation, master equation, should hold. And then we have a cohomological condition, which is kind of what makes the construction essentially unique, is that the cohomology sheaf of that guy is 0 in negative degree. So this is a complex of sheaves which is concentrated in non-positive degree, and we want that the negative part has 0 cohomology. And this we call a BV variety. Right. So in this definition, and so the main theorem will be that starting from S0, you can construct essentially uniquely an S with this property, and so you have a kind of canonical BRST complex, which is a sheaf of differential P0 algebras. And so here we didn't say anything about critical set, but the first result is that this contains the information about the critical set of S0, and this is what I want to say next.
Could you say a couple of words of what's the motivation for the third condition? What's the meaning for the third condition?
Yeah, I don't quite know. So it is something like a resolution, that you are constructing some resolution, and resolution usually tell you that some cohomology vanishes in some degree. So you can also say different from 0 because there is no cohomology in positive degree. But in practice it will be what you need to construct recursively S out of S0. So there will be a perturbations or cohomological perturbations theory to construct S out of S0 step by step, and there are obstructions, and for that to work you need this to vanish.
In the cohomology in degree 0, it has some meaning?
Yeah, it has some meaning, and also in degree 1, and I will come to this. So let me explain the cohomology in degree 0 at this point, and later, yes?
You said that S at degree 0?
Yes.
how do we have some function, the ideal generated by
I didn't hear the...
You said that S has
Yes.
S0 and then that S is S0 modulo element of positive degree. So
No, but the ideal is the ideal generated by elements of positive degree. So you take an element of positive degree and you multiply by anything you like.
you might have something.
Yes, it has degree in all directions. Right, so the cohomology in degree 0 will be the functions, the invariant functions on the critical set. But for that I have to say what invariants mean. And let me say that. So out of this S0, which is a polynomial in n variable, if you like, you can construct the following map, which is from vector fields, the tangent sheaf, to the functions on X. So this is all classical. It's all about S0, which is a map ds0, if you like, which takes a vector field and maps it to the vector field applied to the function. So the kernel of this map is what we call is a Lie algebra. It is a Lie algebra of infinitesimal symmetry. So these are the vector fields which annihilate the functions. So this infinitesimal symmetry, Lie algebra of infinitesimal symmetry. Which may come from a Lie group action or may not. And the co-kernel, so it will be OX by the image of ds0. So this is what is called the Jacobian ring or something. So you take functions modulo the ideal generated by partial derivatives of S0. So these are functions on the critical sets, if you like. And L, so this is an algebra, a commutative algebra, and L acts on it.
You can move up the...
Excuse me?
You can move it up.
I'm sorry, yes. Right, so these are the classical data associated to a function. You can look at its symmetries, and these symmetries act on the critical set. So this is a simple theorem. Well, so suppose we have such a variety, BV variety. It's a BV variety. We support X S0. Then the first thing is that the cohomology sheaf H of X, well you will take OM and bracket with S, is supported on the critical locus of S0. So it's the points where the derivatives, the partial derivative, all the partial derivatives of S0 are 0. So this is some kind of sub-variety, and this sheaf is 0 outside, on open sets outside this variety. And it also vanishes, maybe it is written here. So Hj is equal to 0 for j negative, and H0 again of OMS are the invariant functions. Did I give it a name? So maybe I didn't. So OX modulo image of DS0, and invariant under the infinitesimal symmetries. So you see that this BV varieties know about the critical set. So before I say something about H1, let me explain the existence and uniqueness result of S given S0. J negative here and J0 here. There is also cohomology in positive degree in general, but none in negative degree. So let me give the trivial example. Which is actually important. So you take X to be a point. So the functions are just the field, and S0 equal to 0. And then you can take this variety V, this this variety, graded variety. We support X. You can take, for instance, K of xy with degree of x equal d and degree of y equal d plus 1, and d is some positive number, say. And then if you the cotangent bundle, maybe these are global sections, I should denote it like this, are K of x, y, x star, y star, completed, and this tag x star is minus d minus 1, tag y star is minus d minus 2, and you can take S to be x star y, that's degree 0. And so this is some trivial example, but you start from something trivial and you do something not very complicated but non-trivial. But you can show that the cohomology, this BRST cohomology, is just trivial in this case, just 0, except in degree 0, which is just a constant. And this is important because if you have any solutions of your problem, namely a BV variety, you can always tensor it by some stupid solution like that, and you will not change the cohomology. You also don't change the complex up to quasi-isomorphism of P0 algebras. So maybe I should say here that, the differential of y star is x star, and the differential of x is minus y in this case, I think. So this is trivial, but you have to take into account these trivial solutions. Right, and now so the existence theorem is something like that. So first of all, so this is a generalization of this story. So if Vs is a BV variety, then you can always construct a new one, which is V cross T and S plus some xi star yi. It could be in an infinite sum, provided you have finitely many variables of each degree. So we support x as 0. Then this is again with same support, and this T is just some affine or graded affine space generated by all these variables xi, yi. And this is again is also a BV variety, and moreover with quasi-isomorphic. PRST complex. So so then you say that Vs and V prime S prime are called equivalent. If there is a symplectomorphism in this graded sense, a Poisson map, I don't know, invertible Poisson map, f from T star minus 1V to T star minus 1 V prime, such that f star of S prime is equal to S. So this is a trivial notion of equivalence, but then you say that they are stably equivalent. If there exist some trivial solutions, like there, so that these are equivalent. V prime. So if they become equivalent after taking the product with trivial solutions. And so the theorem is that given as 0, a function on a smooth affine variety, there exists a BV variety. We support x0, and it is unique up to stable equivalence. Okay, so right. So maybe let me say just a few words about the existence part. And the existence part is actually a classical story. It is due to Batarin-Vilkovisky. Batarin-Vilkovisky explained how to construct such a solution for polynomial functions, and I mean the details were written out nicely in the book of Eno Teitelbaum. However, they have some kind of assumption, some regularity assumption on the critical set, which they don't use, so the proof is really there. So the existence proof is in two stages. The idea is that thing that you have this OM by IM. So just some words about existence, and then is actually, if you have such a BV variety, then OM of IM is actually a resolution of the Jacobian ring. So it's an algebra, so of Jacobian ring, which is OX modulo the partial derivatives of S0. So it is an algebra, a graded commutative algebra, concentrated in non-positive degree, which is free as an OX algebra, and so and its cohomology is concentrated in degree 0, and it is equal to this. This follows, more or less. And so the construction goes in the following way. You first construct a resolution of J as 0, so you start from R. And how to construct a resolution of J of S0 as an algebra was explained by Tate. So it's called Tate resolution. In some special case it is a Koszul resolution. And once you have the Tate resolution, you can reconstruct, no, that is correct. So you can reconstruct the cotangent bundle, and then recursively construct a solution of the master equation starting from S0 using this filtration FP essentially. And to do this recursive construction, what you need is this vanishing of cohomology in negative degree. So this is the existence part. And for the uniqueness part, I will not explain it here. There will be this last step is also explained in a note titled Boym. It says that this recursive construction is unique up to the so-called gauge equivalence, which is a special symplectomorphism or automorphism of T star V. And then what you have to check is that the choice of Tate resolution doesn't matter, and that is more subtle, and I don't have time to explain it here. So maybe I will conclude by something that you guys can solve, some kind of open question, which is an attempt to describe in classical terms what this BRST cohomology is. Now we know that this BRST cohomology is canonically associated to a function of n variables, so you can take a function of n variables and try to compute it, and I have a computer program which does that, and it's usually very complicated even for very simple functions. But for the cohomology in degree 0 and 1, so degree 0 I already described, there one can more or less describe it. And then the second question is also how to describe this Lie algebra structure. So let me see. So let me try to say something about the BRST cohomology in general, and then in degree 0 and 1. So how to compute this BRST cohomology? So we have a filtration, right? So we have a filtered complex, and there is an associated spectral sequence. Then you can go through the spectral sequence, and what you get is something like that. So let Vs be BV variety, We support x as 0. And let me take the global sections of this BRST cohomology. So the first statement is that there is a spectral sequence, fourth quadrant actually. Degenerating at the second term, E2, such that E2 PQ is equal to HP of J of S0, so the Jacobian ring to which you add some variables, beta 1, beta 2, and so on, with some differential D1, which I will not be able to describe. I will describe it for small degree. So the beta I have positive degree. This is for Q equal to 0, and 0 in Q different from 0. And the second statement is that H Vs, so there is some kind of canonical edge homomorphism from this to this, is an isomorphism of graded commutative algebra. So and so there is a little subtlety here that this is naturally an algebra, but not Lie. So there is also a bracket, but the bracket is not quite compatible with the filtration. So if you take some element of filtration degree P and an element of filtration degree Q, and you take the bracket, you get an element of large degree, of large filtration degree, if P and Q are large, but it is not P plus Q. It can be less depending on the monomials that you take the bracket of. So this will imply that actually the spectral sequence will be okay to compute the algebra structure, but to compute the Lie bracket you have to go through the explicit construction of cosine, at least as far as we can say. So let me say what the cohomology is in degree 0 and 1. So in degree 0 I already said. And this, I think, it will be closer to what you guys are expert of, and of which I don't know anything. So this is about Lie-Reinhard algebra, so Lie algebroid, if you like. Right, so you probably all know what is a Lie-Reinhard algebra. So you have a Lie-Reinhard algebra. So you have a pair AG, where A is a commutative algebra, and G is a Lie algebra. And G acts on A by derivations, and there is some compatibility. And so the main example is a commutative algebra, and there A is the main example. So it obeys the same axiom as derivations of a commutative algebra. And in our case, we have A is functions on an affine variety, and G is equal to L. Okay, and then there is a notion of ideal of a Lie-Reinhard algebra. Maybe I don't have the time to, but you probably know what that is. So an ideal, so you have a Lie-Reinhard ideal, which is a pair I and don't know what is the name here, H. So I is an ideal in A, H is an ideal, Li ideal in G, and there is some compatibility, some kind of natural compatibility. And then you have that A modulo I and H modulo G modulo H with those compatibility is again a Lie-Reinhard algebra. So our example is the Jacobian ring, which is a quotient of A, and L by an ideal L0. So among all the symmetries, there are kind of trivial symmetries of a function, right? So the trivial symmetries are the vector fields of the form psi of S0, eta minus eta of S0, psi, where psi and eta are vector fields. So this will be trivially kill the action, and this becomes some kind of trivial symmetry. So the statement, and probably this is my last statement, I'm not sure I have time to give you the homework. So if you have a Lie-Reinhard algebra, you have something which is called the Ram cohomology of it, or also called Chevalley-Eilenberg cohomology of the Lie-Reinhard algebra. So you have omega of AG, or the Ram complex, which is Hom A wedge G with values in A with some differential D. This is called the Ram complex. The differential is given by the bracket and the action, essentially. Okay, so the theorem, and it's a theorem for low degree and the conjecture in general, is that the BRST cohomology is isomorphic to HP, the cohomology of that thing here. For P equal to 0 and 1. And then there is a question about what is the bracket, and at this level we can only define the bracket at level H0. So recall that the bracket has degree 1, so in particular there is this bracket here. And this you can describe directly in classical terms. So in terms of this data here, let me try to conclude by that. So we have a bracket on this level. You want to, so let's call it the Ram here. Maybe you already know, probably it must be classical, that there is such a bracket, and maybe you also know it for higher degree. And so suppose you have two functions here of degree 0, so you have f, which is an invariant function of in the Jacobian ring, and you want to construct B of f G, which will be a cocycle representing a class in H1, so it will be a map from G, which is L model 0, to A, which is the Jacobian ring. So how to do that? So F is invariant, right? So it means that if I act with so suppose you have some representative here, right? Tau. Let me call it tau. So it will be a representative in L of an element here, and I have to produce an element here. So how do I do it? I take F, I act on it with F. So it is an invariant function on the Jacobian ring. So it will be 0. It will be a function on X, which is 0 modulo the ideal generated by partial derivative. So this will be a vector field psi depending on F and tau acting on S0. And so non-unique, of course. And then you can do the same thing with G. and actually this B of Fg will be psi F tau on G minus psi G tau on F. And you can check that the class is independent of all the choices that you have to make, and that this is a Lie bracket. So two questions are, did you know about does it exist for higher degree? And the more crucial question for us, because it is rather embarrassing that I have no examples so far where this bracket is non-zero. So the question is there an example, or can you prove that it is always zero? It should be a little strange, because it means that the bracket on cohomology is always zero, and there are never obstructions to deforming solutions of the master equation at this level. Thank you.